welcome to today's Friday Happy Math Hour. Today we're going to cover vectors, which is sections, I believe 6.3 and 6.4 for the pre-cal 2 course. Okay, before I begin, guys, vectors are very important, guys, for Calculus 3. In Cal 3, everything that we go over today in vectors, they're going to cover it in chapter 11.1 in Cal 3. Okay, but then you're going to go from plain vectors to 3D vectors. Okay, so I hope this PowerPoint is going to help you understand vectors. Okay, now, hey guys, the main objective for today's section is, I forgot to do the law of sines. This was from last week. Okay, but the main objective is finding component, form, and magnitude of a vector, vector operations, unit vectors, linear combination of a unit vector, direction angle of a unit vector, and vector application problems. This covers 6.3. And then 6.4 is going to be the dot product, angle between two vectors, orthogonal vectors, and the projection of u onto v. Okay. So to begin, guys, as an introduction, this is what vectors are, okay? Quantities such as a force and velocity involve both magnitude and direction and cannot be completely characterized by a single real number. To represent such a quantity, you can use direct line segments, as shown in figure 6.10. Right? There's a line segment. The directed line segment PQ has an initial point P and a terminal point Q. You see that P is my initial point, and Q is my terminal point. Okay. Okay. Now it has a magnitude, which is or the length. And it's denoted by this means magnitude. The symbol, like two vertical lines, and then the PQ, right? And then with the arrow on top, with two vertical lines, that is denoted. That denotes magnitude, and can be found by using the distance formula. Okay. Okay, you're gonna see how the distance formula is very related to using vectors, because we're gonna use the distance formula. But we don't use x1, x2, and y1, y2. We use p1, p2, q1, and q2. Okay, but for now, we're going to use the distance formula just so you know that, and it will make the transition to using p1, p2, and q1, q2. Okay, and also let's see. Also, vectors are denoted by lowercase bold letters such as u, v, and w. You see, they're bold. But at times, when you write it on paper, right? When you do your notes and write it on paper, it's hard to put bold on. When you're writing on paper, right? That's why this is how you denote it: U with a letter arrow on top, or V with a letter arrow on top, or W with an arrow on top. Okay, this is another form to represent vectors. Okay, two vectors are equivalent if they have the same length and direction. In other words, you need to find the magnitude, which is the distance, and the slope. Again, magnitude, right, is denoted by the symbol here, like those two double lines, vertical lines, PQ with an arrow on top, and the other two vertical lines. That's the symbol for magnitude. Okay, so PQ, right? So this is magnitude, is the same thing as my distance, and the distance formula is the square root of x2 minus x1 squared plus y sub 2 minus y sub 1 squared. We also need to know the slope, right, from pre-cal. The slope of PQ is equal to y2 minus y1 over x2 minus x1. So the first example that we're going to do, you have to show that two vectors are equivalent. Okay, by equivalent, they have to have the same, the same length or magnitude and the same direction. Okay. For example, okay, so it says here, show that u and v in figure 6.12 are equivalent. So solution, we need to find the magnitude, which is the distance, and the slope of each vector. So there's my distance formula again, and there's the slope formula. Okay, now, we're going to let u, right, because u is the line segment PQ, so we're going to let u equal to PQ, so vector PQ. And we're going to let v be the vector RS. Okay. Okay, now, let's first start with P and Q. Okay, we're going to find the distance and then the slope. So if you notice, x1, right, is going to be 0 because if this is my initial point, my first point, my x1 and my y1 are both 0. And x2 will be 3, and y2 will be 2. Okay, so all we're going to do is plug into the formula, right? So my distance is x2 minus x1, which is 3 minus 0 squared, plus y2 minus y1 squared. Okay, this will give us 3 squared plus 2 squared, which will give us 9 plus 4, which will give us the square root of 13. So the magnitude or the length or the distance, PQ or vector V, and by me vector U, is equal to the square root of 13. Now let's find the slope of PQ. Okay, so it's going to give us, so y2 is going to be 2, right? So it's going to be 2, y2 minus y1, which will be 2 minus 0. And x2 minus x1, which will be 3 minus 0. So it's going to give us 2 over 3. So for vector u, which is vector PQ, my distance or the magnitude is the square root of 13, and the slope is 2/3. Okay, I mean slope, guys, is almost like the direction, right? Because it's going in the I mean that's like my direction. Okay, now let's do the same thing for vector V, which is vector RS. X1 is going to be 1, y1 is going to be 2, x2 is going to be 4, and y2 is going to be 4. So let's plug him into the distance formula. Right, so the distance formula is going to be x2 minus x1, which will be 4 minus 1, and y2 minus y1, which will give us 4 minus 2. This results in the square root of 3 squared plus 4 plus 3 squared plus 2 squared, which will give us 9 plus 4, which will give us the square root of 13. Now for the slope, right, it's going to be y2 minus y1. So my y2 is 4, so it will be 4 minus 2 over x2 minus x1 over 4 minus 1, which the result will give us 2/3. You see, guys, so these, we're showing that these two are equivalent vectors because they have the same length and they have the same slope. Okay, that's how you verify them. Okay, now comes, it's called the component form of a vector. There's two ways that you can present vectors, as component form or linear combination form, which we'll get into linear combination form later on this presentation. So it says here, the component form of a vector with initial point P, right, is P1, comma P2, and the terminal point is Q1, comma Q2. Is given by, right, so this is a formula, guys, to find the component form of the vector. Is equal to, hey guys, the symbol like that, guys, like it looks like a lesson, right? But this symbol, guys, denotes vector. Okay, if you put parentheses, it's going to be wrong. It's going to be the symbol here, guys, like the symbol is equal to Q1 minus P1, comma, and Q2 minus P2. Right, so if PQ is represented by vector V, then Q1 minus P1 is called component 1, component V1, and Q2 minus P2 is called component V2. Okay. Now, the magnitude or length of V, of vector V, is given by, right, this is a symbol for magnitude, so the magnitude of V is equal to the square root of Q1 minus P1 squared plus Q2 minus P2 squared, which is equal, right? Again, Q1 minus P1 is component V1, and Q2 minus P2 is component V2, right? So if we want, when we find the component form of the vector to find the magnitude, all we do is plug in the component V1 and component V2 and square both under the square root, and then there'll be my result. It says here, if the magnitude V is equal to 1, then V is a unit vector. Moreover, if the magnitude of V is equal to 0, if and only if V is a 0 vector. V is a 0 vector of which is 0. Okay, now guys, I know if this is your first time doing vectors, this seems a little bit confusing, but once we start doing some examples, it's going to make a lot more sense. Okay, now need to use initial point. So point P, guys, is the same thing as point 1, right? This is the same thing as x1 and y1, right? Point 1 is x1 and y1. So instead of using x1 and y1, we're going to use P1 and P2. That's for the initial point. And for the terminal point, Q is going to be lowercase q1 and q2 instead of the point 2, which is x2 and y2. For the magnitude, which is a distance formula. Okay, for example, so you can see the connection. This is point 1, right, and point 2. This initial point is P1 and P2. And the terminal point will be Q1 and Q2. So let's plug him into the distance formula, right? So, but this is what we're going to be using instead of the distance formula that we use in pre-cal 1. We're going to be using the magnitude symbol of this means vector PQ. Okay, so we're going to be using parentheses Q1 minus P1 squared plus Q2 minus Q2. This is supposed to be a 2 there. I guess I made a mistake there. It's supposed to be Q2 minus P2 squared. Okay, that's wrong right there. It's supposed to be a 2 there. Okay. And again, right, once you get the first component, you can call it component V1 and component V2. There's supposed to be a 2 here also. Okay, now, let's see here. Example, find the component form of a vector. This is here, find the component form, they want to find the component form and the magnitude of a vector V that has the initial point 4, 7, 4, -7, and the terminal point, -1, 5. So solution, right? We're going to let initial point P, 4, -7, be P1 and P2. And we're going to let the terminal point Q, right, be Q1 and Q2. -1, 5 will be Q1 and 5 will be Q2. And 4 will be P1 and -7 will be P2. Okay, this is a formula, right, to find the component form. So Q1 is going to be -1 minus 4. And P1 is 4, P2 is -7, and Q1 is -1, and Q2 is 5. So it's going to give us Q1 is -1 minus P1, it will be -1 minus 4, and 5 minus -7. The result will give us -5, 12. This is a component form of the vector. Again, it's crucial for you guys to write it like this, guys, with those slanted lines like that, guys, because if you put parentheses, it's wrong. Parentheses means it's going to be a point. You see, it's not a point. So this is a symbol for a vector, for the component form. So the component form of V is the vector -5, 12. Now for the magnitude, right? So for the magnitude, I already found component V1 and V2. So instead of plugging all this again on the formula, we use the second formula, which is the magnitude of V is equal to the square root of V1 squared plus component V2 squared. Okay, so it's going to give us the square root of -5 squared plus 12 squared, which will give us 25 plus 144, will give us 169. So the magnitude or the length of vector V is equal to 13. Okay. Let's see, just for another example. Okay, now this is number 20 from the book, from the homework. Okay. Hey guys, right now, after I do this example, I'm going to show you an observation, guys, which is very, very easy to use. And now my students from Cal 3, they use the observation, okay? It's like, it's like an observation. Okay, but I'm going to prove the observation to you right now after I do this one. That way, after that point, we're going to be using the observation, okay? Again, so we do the same thing as before, right? P1 is 17, and P2 is -5. Q1 is 9, and Q2 is 3. Right, so it's going to give us the vector PQ is equal to Q1, which is 9 minus 17, comma, and then Q2 minus P2 will be 3 minus -5. So the result is going to give us -8, comma, +8. Now, when we found the component form, it's very, it's easier to find the magnitude. Right, so all we do is plug in the -8 for component V1 and 8 for component V2 in the formula. So we're going to have the square root of -8 squared plus 8 squared will give us the square root of 64 plus the square root of 64, which the result will give us the square root of 128. Okay, but here, guys, we have to simplify this. Okay, so this simplifies to a square root of 2. Some of you guys might be thinking, how do you go from the square root of 128 to a square root of 2? Well, here's how. Right, so you have to find the factors of 128. And the highest factor, that's a perfect square, that's a combination we're going to use. Okay, so I know that 128 is 64 times 2. I mean, the square root of 64 times the square root of 2. The square root of 64 is equal to 8. So it's going to be 8 square root of 2. Okay, that's what you got there right there. I believe in WebAssign, I think WebAssign wants you to simplify it all the way through on your homework. Okay, I'm not sure, but I think they do, because most instructors, they want you to simplify. Okay, if you leave it like that, they'll probably take some points off. You have to go all the way through. Okay, guys, here's the observation, okay, for finding component form of a vector. Okay, now, okay, so here's a proof, right? Check this out, right? So the vector PQ is equal to the component form of Q1 minus P1 and Q2 minus P2. Okay, here's what I'm going to do. This is my initial point is P, and my terminal point is Q. Okay, it's going to be the terminal point minus my initial point. Okay, again, this is Q1 minus P1. So here, guys, with this minus, I'm going to switch the signs on the initial point, and then you just add them up and down vertically. You add them, and it becomes a vector. You see, guys, it's your vector Q1 minus P1 and Q2 minus P2. Okay. Example here, guys, we're going to do the observation, okay, guys, because you're going to see how easy it is. All right, so you start with your terminal point minus, right, my initial point. So we 9.3. Okay, so here, guys, you can even do it faster. Here, guys, I already switch the signs here, right? Because that's what you do, right? Because with a negative, the signs on point P, you switch the signs on the first, on the X and Y value. So this becomes negative 17, and positive 5. And now all you do is add them, and it becomes a vector. 9 minus 17 is negative 8, and 3 plus 5 is 8. This is the one that we did on the previous slide. Okay. Now, again, observation, terminal point minus the initial point, right, results in the vector. Which, if you want it easier, terminal point, you switch the signs on the initial point, and it becomes a vector. That way, you don't have to do the step the step where you switch the signs. You can just switch them when you write it down, and then all you do is add them. Okay, I'm going to do this one here. Okay, that way you know how simple it can be. Okay, there's the observation. So terminal point, Q, which is negative 8, negative 9, right? Mine is right here, guys. I already switched the signs, right? The initial point is 1, 3, so I switch the signs. It'll be negative 1, negative 3. We add them, and it becomes a vector. Negative 8 minus 1 is negative 9. Negative 9 minus 3 is negative 12. So this is my component form of the vector. My students in Cal 3, they love this observation because they can get the component form and the magnitude like within a minute. Okay, instead of struggling by trying to follow the formula, because I know it's a big transition going from X and Y, what we've been accustomed to P1 and to P1, P2, and Q1 and Q2. Okay, but with the observation, guys, it's gonna the transition will be much smoother. Now for the magnitude, right? I already have the component V1 and V2, so all we do is plug them into the formula. Will give us the square root of negative 9 squared plus negative 12 squared. Will give us the square root of 81 plus 144, which will give us the square root of 225, which results, I believe, in 15. So that's my magnitude, 15. Now, there's also vector operations. Okay, you can add vectors, you can multiply by a scalar, or you can subtract vectors. Okay, and here's the rule. It says here, let vector u equal to in the component form. This is component u1 and component u2, and v equals to component v1 and component v2, be vectors, and let k be a scalar. Then the sum of u and v is a vector u plus v. You can add the first components, u1 plus v1 and u2 plus v2. Okay. Then if you have a scalar, say you multiply it by k, it's going to be k times component u1, comma, and k times component u2. Because I also have another observation for this one here. Okay, but first let's do it the way the book does it. Also, guys, the negative vector of v, right? Say v is equal to component v1, comma, component v2. So a negative, you have to turn into a positive. Okay, guys, like negative v is equal to negative 1 times v. Okay, so it will be negative component v1, comma, component, negative component v2. And the difference of u and v, right? The negative turns into addition, and the vector becomes negative, both components. Okay. Again, guys, this is a vector u1 minus v1, right, for the difference, and u2 minus v2. Okay, now let's do some examples here. Example number 3, it says let v equal to component negative 2, comma 5, and let vector w equal to component 3, comma 4. Find each vector. So we have to find 2v for A, for B, w minus v, for C, v plus 2w. Okay, so let's try it first. Okay, so right, so the 2 is a scalar, right? So I got 2, and I got the vector. The vector v is negative 2, 5. So what we do is multiply the 2 times negative 2 and 2 times 5, which will give us negative 4, 10. Okay. Now these guys, you have to graph them. Okay. When you add them or subtracting, you have to graph them. Okay. Now here's, I believe, is the easiest way to graph it. Right. You first start with a vector. Right. This is vector v, which is negative 2, 5. Right. Negative 2, 5 is a point there. Right. So that's my vector. And then, right, you're gonna get another negative 2, 5. Because remember that to find the direction of the vector, remember we use the slope. So the slope is the change of y over change of x, correct? So this is my y is going to be like 5 units up. So from here, guys, where it ended, I'm going to go 5 up. And then the negative 2 means I'm going to go to the left 2 units. You're going to go 2 to the left. Right. So when you do that, guys, that's how you go from here to here. Where it ends. That's the way you should graph it. Okay. Okay. Now let's try B now. The vector w minus vector v. Okay. So vector w is 3, 4 minus vector v is negative 2, 5. Remember the rule, guys. This has to become addition, right? If it's addition, then the two components on vector v, you switch the signs, because negative times a negative will give you a positive, and negative times a positive will give you a negative. And now you add, it's going to be right. You can add the first components, like 3 plus 2, comma 4 minus 5. So the answer will be 5, negative 1. Okay, now guys, here's the observation. Okay. Because in the observation, guys, it's always wise to put them vertically. Why? Because this way they already set up to add both components on the first slot, and then add the components 2 on the second slot. Okay, let me show you how it's done. Okay, so this is vector w, gives us 3, 4, right? Minus v, right? Means here, guys. Okay, here I show like an extra step here. Okay. Okay, this right minus vector v means minus, right? This is my vector v, which means on the minus vector v on the v vector, I have to switch the signs, so it becomes 2, negative 5, right? And all you do is add them, so it'll be 3 plus 2 is 5, and 4 minus 5 is negative 1. So that's, you see, we got the same thing, because this way this is more visual, right? If you put them vertically. Okay, now you can go, from here, guys, you don't have to show this step. You can go straight from here to here, guys. For example, right, this is vector w, component 3 and 4. And then because it's minus, on vector v, you're going to switch the signs. So that becomes 2 and negative 5. And then all you do is add them. Okay. And here's a graph, okay, for that one. check this out, guys. Since W is first, right? So we have W first. So you go from the origin because it's got to be in standard form. So it goes from the 0, 0, right? It goes to the point 3, 4, right? Because vector V is 3, 4. Okay, now, yeah, right? So it's going to be 2, negative 5, correct? Because vector V, right? When you subtract it, it becomes 2, negative 5, which means, right? It's going to go right. We first do the second component. It's going to go down 5. From where? From here. It's going to go, right where it ends at 3, 4, it's going to go straight down 5. Then it's going to go 2 to the right. Right? This way you connect, once you put the vector W, right? And then once you do you go down 2, you go down 5 and 2 to the right, and then you connect where it ends to where it is over here. And then you do is connect. This answer, guys, will be the W plus negative E. Or you can do it another way, okay? This is the way it should be done. But if you want, because at times this is kind of confusing, at times, guys, just do the first vector, right? Vector W will be 3, 4, so you're going to go to 3, 4. Okay? Then we know that the answer is 5, negative 1, right? So we're going to go to 5, negative 1. So 5, negative 1, right? So that's this vector here. And in this one, guys, all I would do is connect it from where it ends on both vectors. And that's my graph. Okay? If you want to do it that way, but the right way to do it is how I showed you. Okay, now let's do part C. Okay. So we have V, right? So vector V is negative 2, 5 plus 2 vector W, and vector W is 3, 4. Okay, again, this is the way the book does it. Right, so here they distribute the 2 because 2 is a scalar, so 2 times 3 is 6, 2 times 4 is 8. Now you can add them, right? So you can add the first components, would be negative 2 plus 6 and 5 plus 8. The answer is 413. But again, I believe this way is easier if you put it vertically. Okay, again, the observation. Right, so first I'm going to put vector V, right? And vector V is equal to negative 2, 5. Then plus 2W, right? So I'm going to put 2 times vector W. So vector V we just slide it over. Here we distribute. 2 times 3 is 6, and 2 times 4 is 8. So we got the vector component 6 and 8. And all we do is add them vertically. We have 413. Okay, guys? But you can go straight from here, guys. Instead of showing the step, you can just multiply the 2 times the 3 and the 4. You can go from here to here, to the second step, and get the answer. Okay, now how do we graph this? Okay, here's how we graph it. Hey guys, what was first? What was the first one? It was vector V, right? So vector V is negative 2, 5. So we're going to go from 0, 0 to negative 2, 5. There it is. This is vector V. Now we're going to go to 2 times vector W, right, which is 6 and 8, which means from here, right, it's going to go up 8 and 6 to the right because they're both positive, right? So you will go 8 up and 6 to the right, and you put a point there and you connect them, and that'll be 2W. And then to get the answer, guys, you go from the origin to the end of a vector 2W, and this is your graph. Okay, now comes unit vectors. Because unit vectors means that the magnitude is equal to 1. Okay, after you find the component form of the vector, then the unit vector must be equal to 1. Okay. Example number 5. Example 5 says finding a unit vector. It says find a unit vector u in the direction of v, and the direction of vector v is equal to negative 2, 5. Then it says verify that the magnitude of u is equal to 1, right? And the magnitude means distance. Okay, so here's my solution. I need to find the magnitude of v, right? Because this is my formula here, guys. That's my formula. Okay, the formula will be the vector v over its magnitude. So I already got the vector v. So all we need is the magnitude. So it's going to give us the square root of negative 2 squared plus 5 squared. Will give us 4 plus 25. Will give us the square root of 29. So I already found the magnitude. Okay, right? This is my formula, right? From here, the unit vector. So unit vector, right, is equal, right, vector v was, or is the component form of negative 2, 5 over the square root of 29. So this is equal, right? This is a scalar, right? It's like 1 over the square root of 129, right? Which will give us negative 2 over the square root of 29, and 5 over the square root of 29. So this is my vector that we're looking for. But now we need to verify that this is equal to 1. I mean the length. Okay, let's do that. Okay, now guys, here, right? The magnitude of u is the first component, negative 2 over the square root of 29 squared, plus 5 over square root of 29 squared. This will give us 4 over 29, and this will give us 25 over 29. Right? When you add them, it's going to give us the square root of 29 over 29, which is equal to 1. Okay. Let's try another one of those. This is a checkpoint from the book. Same procedure, right? So we need to find the magnitude of v. There's my formula. And there's to find the magnitude, right? So this is what we need, right? So we only need the magnitude of v. So v equals to the component 6 comma negative 1. So for the magnitude, it's going to give us the square root of 6 squared plus negative 1 squared, which will give us 36 plus 1 will give us the square root of 37. Okay. So vector v, right, is 6 negative 1. And the magnitude is the square root of 37. So this becomes 6 over the square root of 37, comma, negative 1 over the square root of 37. That's my unit vector. Now to verify it, that is equal to 1. Okay. So, right, so we're going to plug in into the magnitude formula. It's going to give us 6 over the square root of 37 squared plus negative 1 over the square root of 37 squared. This will give us 36 over 37 plus 1 over 37. And the result is 37 over 37, which is equal to 1. That's how you verify it. Okay. And again, unit vector means 1. Because remember the unit circle, guys, also with the unit circle? The unit circle means also it goes all the way only to 1, 0, 0, 1, negative 1, negative 1, 0, and 0, negative 1. Okay, now there's another form to write a vector. This is called linear combination form of a vector. Okay, all this means, right, if you have vector v, right, vector v is component v1, component v2. So component v1 is going to be, the first is going to be component v1, 0, plus 0 component v2, right, because if we add them, we get v1 and v2, right, but now they don't want you to put in component form, so they want you to put I and j. Okay, they're going to put I for component v1 and j for component v2, right? Which means this is a vector, right? Vector j is 0, 1, and vector I is going to be 1, 0. Okay, guys, this is not that complicated. Okay, let me show you an example how simple this is. Say this is called, right, the component form of v. So for the linear combination, I would do is, right, negative 5i plus 12j. Okay, so this is called linear combination form. The one on top is called component form. Okay, now guys, please do not do the mistake that you put, right, the component form like negative 5i, comma, and 12j. That's a mistake that students make all the time. Please don't do that. The linear combination form, it doesn't have the component form. Like those lines right there. Like the greater than and less than symbol. Okay, that's what it seems, right? Don't mix them up. Again, this is component form, and this is linear combination form. I believe linear combination form is used in calculus 3. They use that, and also in physics because they use the I and the j components. Okay. Okay, now writing a linear combination of a vector, of a unit vector. Let u be the vector with initial points 2, negative 5, and terminal points of negative 1, 3. Write u as a linear combination of the standard unit vectors with I and j. Okay, so again, let's use the observation as before, right? So it'll be terminal point. My terminal point is negative 1, 3, which is point Q. And point P, right, we're going to switch the signs. So it's going to give us a negative 2, 5, right? So now we add it, and it becomes a vector. -1 minus 2 will give us -3, and 3 plus 5 is 8. Now, they want us to put it in into linear combination form, right? That's component form. Now this is linear combination form. That's it. Okay, so all we do is go from component form to linear combination form. Because when I was taking Cal 3 and there at DPCC back in 2000, I think 2007, I had a hard time with I and J. Why? Because I got so used to X and Y. And I talked to my instructor and I told him my situation. He goes, no, but you just put it in component form all the time. And then if it wants it in linear combination form, then at the end you go from component to linear because it'll be much easier. So that's what I did back then. But now most students, they're already used to using I and J because they use it in physics. Okay, but if you struggle with that, you can always put it in component form and then change it to linear combination form if it wants it in that form. Okay, now comes vector operations, right? But it's going to be the same thing as before, but now it's with I and J. Okay, now, solution. It is necessary to convert U and V to component form to solve this problem, right? Because at times, what I would do, I would convert it to component form, right? Because it says you don't have to. Just perform the operation with the vectors in unit vector form, okay? This is from the book, and right now I'm going to show you my way, okay? This is what the book says. So 2u minus 2 times vector u minus 3 times vector v is equal to 2, right? It's going to be 2. That's my scalar. And vector u is negative 3i plus 8j minus 3. That's my scalar. And vector v is 2i minus j. Okay, so I distribute 2 times -3 is -6i. 2 times positive 8 will give us -16j. -3 times 2 will give us -6i. And -3 times -j will give us positive 3j, right? And then we add the i's and j's separately, right? So the i's is going to be -6i minus 6i will give us -12i. And 16j plus 3j will give us 19j. Now again, I believe it's easier, guys, to work them out vertically, okay? So 2 times vector u is equal to 2, right? Times vector u. Vector u is -3i plus 8j. When we distribute, it's going to give us -6i plus 16j. Then comes minus 3 times vector v. So right, so vector v will be -3 times 2i minus j. Now we distribute, so -3 times 2i will give us -6i. And -3 times -j will give us positive 3j. Now here, guys, right, we add them because they're already set up with the i's and the j's with the j's. Will give us -12i plus 19j. And again, I truly believe this is an easier way to do it. I believe the instructors, it doesn't matter how you do it, but just get the answer right. Okay. Okay, now here we're doing the finding direction angles of a vector. So direction angles, guys, you have to know the quadrant that is on. Okay, because this is a formula, guys. The formula will be the tangent of theta equals to b over a. Now, what's the b and what's the a, guys? The a is with the I. It's ai plus bj. So, for example, on a, right? First thing we have to know, guys, is what's a quadrant, right? It's quadrant 1 because they're both positive, right? Positive means quadrant 1. Okay, now, so we're going to plug into the formula. So it's going to be the tangent of theta is equal to 3 over 3 because it's the one with the j is a b, so it'll be 3 over 3, which is equal to 1. Now, how do we solve it? We take the arctangent of both sides. So theta equals to the arctangent of 1. Okay, where's the arctangent equal to 1? Right? If you put that into the calculator, guys, how it is, it's going to give you 45 degrees. So that's your answer. Okay? Now, because it's in quadrant 1, it stays in quadrant 1. Okay? And here's the sketch I was talking about, right? So this is my vector, right? And this is 3i plus 3j. We see, guys, because it's right in the middle, right? It's like 45 degrees, remember, from the unit circle? So that's why this is 45 degrees. Now let's try B. Okay. Here's on B. Again, right? So it's going to be, right? So it's going to be the arctangent of theta will be equals to negative 4 over 3. First of all, right, it's going to be quadrant 4 because it's positive and negative. So if it's quadrant 4, right? If it's quadrant 4, at the end, you need to add 360 degrees to theta because you're going to get a negative answer. Because quadrant 4, the tangent is negative. So you add 360. You know, guys, I should have put there, guys, for every quadrant 1, whatever. If it's in quadrant 2, you can add 180 degrees. If it's in quadrant 3, right, you're also going to add 180 degrees. So if it's in quadrant 1, you don't add nothing. Quadrants 2 and 3, you can add 180 degrees. Quadrant 4, you can add 360. Okay, so then this is quadrant 4. At the end, you're going to add 360. Right, so theta is equal to the arctangent of negative 4 over 3. So you put that into the calculator, guys, it's going to give you something like approximately negative 53.1301023.5 degrees. Okay, I think you want to round it off to 2 places. But before we get the answer, guys, we have to add 360. And then we round it off to 2 places, guys. It's going to be 306.87. And here's the graph, right? This is my point, 3, negative 4, which means it goes all the way around. And white is in quadrant 4. Hey, guys, so this angle here, guys, this angle here is negative 53.13 degrees, right? But the angle that we're looking for is the one in red. Well, this angle is the one that we're looking for. That's why you add 360, okay? Okay, now, guys, finding the velocity vector. It says here, find the component form of a vector that represents the velocity of an airplane descending at a speed of 100 miles per hour at an angle of 30 degrees below the horizontal, as shown in figure 6.21. Okay, so there's my plane, right? It's going down at 100 miles per hour, and it's 30 degrees below, right? So if it's 30 degrees below the horizontal, right? This is 180. 180 plus 30 will give us 210. Okay, the velocity of the vector v is the magnitude of 100, and the direction of the angle is 210 degrees. So this is a formula, guys, to get the answer right. The magnitude is 100, and theta is 210. Okay, so we're going to plug in 100 for the magnitude, and then 210 for theta. Now you have to know, right, what the theta is. What the angle is of 210. This comes from the unit circle. The unit circle, right? This is going to be quadrant 3. So 210 degrees is going to be negative square root of 3 over 2, comma, negative 1/2. So the x part is going to be my cosine, and the y part is going to be my sine. So this becomes 100, right, times negative square root of 3 over 2i plus 100 times negative 1/2 j. So this is my result, guys, equals to negative 50, the square root of 3i minus 50j. Okay, now, right, so this is my result. This is my vector that we're looking for. That's a component form. Okay, now there's something extra. Okay, note that v has a magnitude of 100 because, right, if we take the magnitude of our solution vector, it's going to give us 100, right? Because it's going to be negative 50 squared root of 3 squared plus negative 50 squared. It's going to give us 7,500 plus 2,500, which is equal to 10,000. The square root of 10,000 will give us 100. See, guys. So when you take the magnitude, it should be equal to the speed, which was 100. Okay, now this is a start of 6.4. It's called the dot product of u, the dot product of u and v. Okay, say you have vector u is equal to component u1, comma, component u2. And vector v is component v1 and component v2. So this means the dot product. Okay, so the dot product of u and v is equal to u1 times component u1 times component v1 plus component u2 times component v2. If you notice, guys, this doesn't give you a vector, guys. The dot product will give you a scalar or a number. Okay. So again, for these ones, guys, I also have another observation, guys, okay? Because it's always nice to put them vertically because it's easier to do. Okay, look at A part. Okay, let's do A first. Okay, according to the rule, right? So it's going to give, this will be 4 times 2 plus 5 times 3 according to the formula. Which gives us 23, right? A plus 15 is 23. Now look at B. It's going to be 2 times 1 plus negative 1 times 2, which will give us 2 minus 2, which will give us 0. And look at C. This will give us the dot product of U and V will give us 0 plus 4, right? Plus 3 times negative 2, which will give us negative 6. That's my answer. Now here's the observation, guys. Okay? Right? They're saying that the dot product of U and V, right, is here. It means is U1 component U1 times component V1 plus component U2 times component V2. Okay, here's the observation. So again, guys, I'm going to put in vertically. There's vector U, there's vector V, right? So we're going to multiply them see vertically. So U1 times V1 plus U2 times V2. Example, right? Let's do A real quick. So this will give us equals to 4, 5, right? Because it's a dot product. Let's put vector V on the bottom, 2, 3. We're going to add 4 times 2 is 8. 5 times 3 is 15. So the answer is 23. You see, guys, much easier than doing it this way. Okay. These are properties of dot products. Okay. If you have, it says here, let vector U, V, and W be vectors, and let C be a scalar. If you have vector U dot product vector V is equal to vector V dot product vector U. This applies the commutative property. If you have vector U dot product parentheses V plus W, vector V plus W is equal to U dot product V plus U dot product W. This is called a distributive property. Now this is a scalar, okay, the associative property. If you have a scalar times the dot product of U and V is going to be equal to C times vector U dot product V or vector U dot product C times V. Now 0 dot product of vector will give you 0. You have the vector V dot product vector V is equal to the magnitude squared. Okay, now, example 2. This is from section 6.4. Using properties of the dot product. It says let vector U equal to 1, negative 1, 3. Let vector V be a component form 2, negative 4. And let vector W equal to components 1, negative 2. Use properties of the dot product to find. Okay, so for A part, let's do A part first. Right, again, we're going to do the observation for the vectors, right? So here we go, guys. So first, I'm going to do the dot product of U and V. So vector U is negative 1, 3. And vector V is component 2, negative 4. Right, so I'm going to multiply negative 1 times 2, which will give us negative 2. And then I'm going to multiply 3 times negative 4, will give us negative 12. The result is negative 14. Right now, right, so the U dot product V is negative 14. Now we just bring the vector W. And vector W is components 1, negative 2. Now we distribute, so it's going to give us negative 14 and positive 28. That's the answer for A part. Okay. And let's do B. It says U dot product 2V, right? So first, let's do the scalar 2 times vector V first. Which is be 2 times vector V is 2, negative 4. So if we multiply that, it's going to give us 4, negative 8. Now, let's do the dot product of both. This is vector U, negative 1, 3. And vectors 2 times vector V, right? And the dot product will give us 4, negative 8, right? Again, we put in vertically. We multiply negative 1 times 4 is negative 4. And 3 times negative 8 will give us negative 24. We add them, will give us negative 28. Now for vector C, guys, is something that we should know by now, right? That's only the magnitude for C part. So the magnitude of U, guys, is just the magnitude will be vector U is -1, -1, 3. So it's going to be -1 squared plus 3 squared. give us 1 plus 9, or give us the square root of 10. That's your answer. Okay. Now comes the angle between two vectors, guys. Because I know we only have about 8 minutes left, guys, but these two sections, they carry like a lot of material. Okay, a lot of material. So I'm trying to give you what I think is the most important, for each section. Okay. Okay, angle between two vectors. If theta is the angle between two non-zero vectors, u and v, then this is the formula, guys. The cosine of theta equals to the product of u and v over the magnitude of u times the magnitude of v. Okay. And here's the angle, right? Here's the angle that we're looking for. And this is easier to plug into the calculator, guys, right? So here, guys, I just multiply by the arc cosine on both sides, or the inverse. So theta equals to the inverse cosine of the dot product of u and v over the magnitude of u times the magnitude of v. So here's an example. Find the angle between two vectors. So solution, guys, I need to find the dot product of u and v, and also the magnitude of each vector. Okay. So this vector u, right, dot product vector v, by doing the observation. So give us 12 plus 15 will give us 27. So I know this part is 27, right, already. Now just find the magnitude of u. Will give us the square root of 4 squared plus 3 squared. Will give us the square root of 25, which will give us 5. Now the magnitude of vector v is equal to the square root of 3 squared plus 5 squared. Will give us 9 plus 25, will give us the square root of 34. That can be simplified, so it stays how it is. So I found all the missing variables to plug in. Right, so the theta is equal to the arc cosine of 27 over 5 times the square root of 34. Now put it to the calculator. You're gonna get something like 22.17 degrees. So that's how much the angle between the two vectors will be. Okay. And there's my drawing. You see there's the 3, 5, the vector, this is vector v, this is vector u. So the angle is 22.17 degrees. Okay, now, hey guys, this guys is very crucial for Cal 3, okay, because you have to know if the vectors are orthogonal. Because orthogonal means that they're perpendicular. Okay, that's another word for perpendicular. And here is how you know if they're perpendicular or orthogonal. The vectors u and v are orthogonal if and only if u dot product v is equal to 0. Okay. So here, example 4, determine orthogonal vectors. Determine whether the vectors u and v are orthogonal. Okay, so what I would do is do the dot product. Again, when you're going to do the observation. So it's going to be vector u is 2, negative 3. And vector v is 6, 4. So the dot product, right? Well, okay, what we're going to use is going to be 2 times 6 is 12, plus negative 3 times 4 is negative 12. So it's equal to 0. That means that these two vectors are perpendicular, or they're orthogonal. Okay, that's all you have to do. And there's my drawing. There's a picture of those. You see they're perpendicular. Now this, guys, is where it begins this will apply to the word problems, guys. Okay, I think I'm only going to do one because for lack of time, but this is crucial to know. Okay, for Cal 3. Okay, now it's a definition of vector components. Let u and v be non-zero vectors such that u is equal to vector w1 plus vector w2. Where w1 and w2 are orthogonal, which means w1 and w2 are perpendicular. And w1 is parallel, right, to v, or is parallel, or it's a scalar of v, as shown in figure 6.28. See, guys, you see this is vector w1, this is w2. So if you add them, guys, both vectors, this is my result. For example, right, say it's w1 squared, right? So this is vector w1. Okay, remember, guys, and then from here, guys, we move up the second vector. You see this is w2. because if this is double, if this length on the left side is equal to the right length, right? So that means this is the same length. So again, this is W1, and then you go up W2, and then you connect them. That's the addition of two vectors. Okay, now it says here the vectors W1 and W2 are vector components, guys. These two vectors are vector components of U. Okay, the vector W1 is a projection of U onto V, and is denoted by W1 equals to the projection of V into U. The vector W2 is given by the vector W2 is equal to U minus W1. Okay, this vector here, guys, comes from here, guys, from the original one. U equals to W1 plus W2, right? If you're solving for W2, we subtract W1 from both sides, you see? So it's kind of obvious. Now, this is a formula, guys, okay, that we have to know. So before I begin to explain the word problems, guys, we have to know about the projection, okay? How to find the projection of V onto U, of U onto V. You see, guys, these are examples. You see, for example, I think I'm going to do this one, guys, later on in an example. But here, guys, this is what it means, guys. How much force is required, guys, for the boat not to go downhill? Same thing here, guys, with the tires. What force is required for this trailer? For not to go go down the hill. So this is all part also of physics, also, guys. But these problems we do them in Cal 3, and also in pre-Cal 2. But before you do that, the word problems, guys, let's do the projection. It says here, guys, let U and V be non-zero vectors. The projection of U onto V is given by, right? This is a formula. The projection of U onto V is equal to the dot product of U and V over the magnitude squared of V times vector V. Okay. So example, decomposing a vector in components. It says here, find the projection of U, which is vector V is components 3, -5, onto V, which is components 6, 2. Then write U as a sum of two orthogonal vectors, one of which is projection of V onto U onto V. Okay. So in other words, guys, first I need to find the dot product, right, of U and V, and then the magnitude square of vector V, and we find all the info. Okay. Again, let's do the observation to find the dot product. This is my vector U, this is my vector V. So we're going to add them, right? So we're going to multiply them and add them. 3 times 6 is 18. -5 times 2 is -10. So it's going to give us 8. Now let's find the magnitude, right? Magnitude of V. It's going to give us the square root of 6 squared plus 2 squared will give us the square root of 40. But you know what, guys? Right by the squared, when we square it, it will just be 40. Okay, so I got the top and the bottom already. So guys, here's the projection of U onto V, right? The dot product of U and V, right? It was 8, right? We got 8. The magnitude of V squared was 40. And this is vector V, which is 6, 2, right? This is vector V. So now, guys, here, right, I think 8 divided by 40 will give us 1/5. So 1/5 times 6 will give us 6/5. And 1/5 times 2 will give us 2/5. So this is my vector, guys. Now, I want you to write it solve for W2. Right, W2 is equal to vector U minus vector W1. Vector U is 3, -5. Right, and vector W1 is the one that we just got, which is 6/5 and 2/5. So if we do the operation, guys, it's going to give us 9/5 minus 27/5. Right, if you do 3 minus 6/5 and -5 minus 2/5, this is my result. Okay. Now here, guys, right? That's what we're going to do right now. It says here, a 200-pound cart is on a ramp inclined at 30 degrees, as shown in figure 6.30. What force is required to keep the cart from rolling down the ramp? Okay, so solution. What do we need? Guys, I need to find vector F, right? I need to find the force and I need to find the force vector and also the V vector. And also the magnitude of W1, guys, is going to be the force required. Okay, so vector F, guys, right, is going to be 0I minus 200J. Why? Because right? Vector F goes straight down, right? Because it's 200, right? This is 200, because it's going down, it means it's negative. So it's going to be 0i minus 200j, which will be negative 200j will be the force due to gravity, which is going down. Okay. Now vector v, right? Vector v is equal to the cosine of theta I plus the sine of theta I. And my theta, the degrees given is 30 degrees. So 30 degrees, guys, on the unit circle is square root of 3 over 2 and 1/2. Which means this is my I, my j, so it's going to be v equals to the square root of 3 over 2i plus 1/2 j. That's my unit vector along the ramp, which is this vector here. That's vector v. Okay, now guys, I need to do, right, is find the projection of f onto v. So there's my formula. So first I need to get the dot product of f and v. Right, that's my f vector. That's my v vector, right? So by applying the observation, guys, right, what's 0 plus 0 times what's 0 times square root of 3 over 2, that'll give us 0. Negative 200 times 1/2 will give us 100. So it'll be 0 minus 100, so it'll be negative 100. So the top part, guys, the numerator is going to be negative 100. Now let's do v squared. Okay, so this is the component vector, right? Well, this is my vector square root of 3 over 2i plus 1/2 j. So the square root of 3 over 2 squared plus 1/2 squared will give us 3/4 plus 1/4, the square root of 3/4 plus 1/4. This will give us the square root of 1, which is equal to 1. So the denominator, guys, is 1. On the example, guys, on the example from the book, they don't show you that. And when I remember when I was taking this class, I was saying, "Hey, pues what happened with the bottom? With the magnitude squared," and I didn't realize because I didn't really know the concept. And the book doesn't go over everything like in detail. Okay. So anyway, guys, that's how you know that the magnitude squared, will give you 1. Right. So it'll be the dot product of f and v, right, which will be negative 100. Over 1, which is give us negative 100, right, times vector v. Right, so now we distribute. This is going to give us negative 50, the square root of 3 minus 50j, because negative 100 times the square root of 3 over 2 will give us negative 50 square root of 3. Negative 100 times positive 1/2 will give us 50. Now, guys, okay, this is vector w, right? But the force, guys, is a magnitude. So let me go to the next slide. Right, so for force, guys, right, I need to get the magnitude of W1, which will give us, right, it's going to give us the square root of negative 50 square root of 3 squared plus negative 50 squared. It's going to give us 7,500 plus 2,500, the square root. It'll give us, okay, I did it again there. I did a mistake. So it'll give us the square root of 10,000, which will give us 100. So it's going to be 100 pounds of force. That's my result, guys. That's how we do these type of problems, guys. So the projection is very important. The projection of F onto V or U onto V. I believe that's it. I want to thank you. I believe I passed my time a little bit, but hopefully it was all worthwhile.
Thank you, Mr. Isasi, for your wonderful presentation. We do want to remind you all about our previously recorded sessions, which are available on our YouTube playlist. Today's session will also be available on that playlist later on today. Also linked is a short survey to help us improve our TVE sessions. Please take time to fill out that survey. Before you leave, I want to share the TVE sessions that we will have next week. We'll be back with Happy Math Hour next week with Math 1332, which will cover arithmetic in different bases in prime numbers. And Math 2412 will cover exam review number 2. At 1 p.m. today, we will have a student success topic. Today will be the Engineering Academy with Dr. Rebecca Escamilla. Thank you all for coming in today. We hope that you have a lovely weekend. If you have any questions, feel free to use the chat box or mic. And have a great weekend, guys.